Hello, my name is Manav Patel, and this is Lab 5 Choose Your Own Adventure. So I chose the Falling Slinky as my lab. So, the purpose of this lab. The purpose of this lab is quite simple. It's to analyze the behavior of a falling slinky, especially the bottom part of the slinky, when released, focusing on its motion and dynamics. Compare the observed physical behavior to predictions made by the computational model, which was made using ClosedScript code. Introduction. So first we'll apply Newton's second law to describe how forces acting on an object influence its motion. Formulas are the position update formula, which is Rf equals Ri plus V average delta t, and velocity update formula, which is Vf equals Vi plus F net over m whole times delta t. So here are the fundamental physics principles that were used in the lab. So first, we'll calculate the drag force using the formula F drag equals negative b times absolute value of velocity squared in the v hat direction, where b is the drag coefficient, absolute value of v is the speed, and v hat is the direction of velocity. The coefficient, the gravitational force is given by F grav equals negative mg, where m is the mass and g is the acceleration due to gravity. The net force can then be found by adding these two forces together, so F net equals F grav plus F drag. So here's a brief preview of the results, where the computational model, which is the model that was made using ClosedScript, and the observed model, which was made using Tracker, were quite similar, indicating that the results were accurate. The system is the slinky and the surroundings is the earth. Here is the observed motion using Tracker. I gathered some data using it. So this is the computation model, the code for it. For initial conditions, the mass was 0.2, the position was 0.141 in the x direction, negative 0.516 in the y direction, and 0 in the z direction. The velocity was 0 in all directions, and the delta t was 1/30th of a second, and g is 9.8. And I found the value for b using trial and error. So in this, from 0 to 5.5 seconds, the bottom part of the slinky was stationary, so that's what we did, while t was less than 5.5. Using weight and the tension force, which is equivalent to each other, which is why the bottom part of the slinky was stationary. And while t was greater than 5.5 and less than 9, that's when the bottom part of the slinky started to move. So we calculated the drag force and the weight, and then we added those two together to calculate the net force, and then we used the velocity update formula and the position update formula to plot velocity and position time graphs. So this is the position versus time graph, and this is comparing those two graphs together from the observed motion and the predicted motion, the tracker and ClosedScript code. So as you saw at the beginning, as you saw in the previous slide, at the beginning when the bottom of the slinky remained stationary, the graphs were identical. However, slight differences emerged as the slinky began to move. Despite these minor variations, the graph remains closely aligned, indicating that no physics errors were present. Although no physics errors were present, other types of errors such as human error in tracking the data could have occurred, and also mistyping the code could have occurred as well. So questions. Why does the bottom of slinky remain stationary in the start? So the simplest explanation for this is that the bottom part of the slinky remains stationary because the forces of the tension pulling upward and the gravity pulling downward are perfectly balanced. This equilibrium ensures that the bottom does not move until the tension force is disrupted, such as when the slinky is released. At that moment, the balance is broken and the bottom begins to move in response to the changing forces. Thank you for listening to me. Have a nice day.